Today we are diving deep into blast furnace operations. Especially, we'll explore how to achieve a stability and efficiency, which are absolutely critical for successful and profitable hot metal production. So first let us define our key term. Process stability refers to continuous and smooth operation characterized by uniform and stable stock descent, preventing erratic burden movement, channeling or major upsets. Think of it as keeping the furnace running smooth. Uh, and once it's run smooth, then we have a process efficiency, and this is primarily measured by a reductant rate. That is a total coke plus injectant used per ton of hot metal. It's also quantified by the gas utilization ATCO, which tells us the percentage of carbon monoxide gas used for reducing the ferrous burden. So higher efficiency directly correlate with lower fuel consumption, saving valuable resources. So why are these concepts so crucial? Long-term stability is essential for maximizing benefit and ensuring consistent output. When a furnace operates efficiently, it directly leads to lower fuel consumption, which means significant cost saving and a reduced environmental footprint. Ultimately, the objective is to produce hot metal with maximum gas reduction and uniform gas distribution, all while minimizing fuel consumption and operational disruption. This approach leads to economical and sustainable hot metal production. Now, coming to our next slide, uh, which is about achieving this dedicated balance of stability and efficiency, is a really big try requiring meticulous control over several key areas. Primarily five main factors are there: burden distribution, raw material quality management, gas flow and permeability control. This is also no less. Thermal control is one of the major aspects, and casting operation above all is important because the technology that we have applied to melt out, it has to taken out efficiently. These elements are the pillars of optimized blast furnace performances. Now, coming to our uh, one by one topics, and in which let's start with the burden distribution, which is considered the primary control tool. Its main purpose is to manage gas flow within the furnace, ensuring that gas flow evenly through the ferrous layer to maximize reduction, and this is how we can optimize our fuel rate. Remember, gas naturally follow the path of least resistance, and that is well known to all operators. Here where coke plays a crucial role. Coke layers are significantly more permeable, about 4 to 5 times less resistance to gas flow than the ferrous burden, and this makes coke an excellent gas distributor, creating controlled passage for the gas flow. And the pressure difference between sequential coke layer is what drives the gas efficiently also through the denser ferrous layer. And so to optimize this primary control, we follow several ideal practices. For higher productivity, we aim for an ore-free center maintained by discharging coke onto inward chute position, typically about 15-20% of furnace diameter. This central coke stabilizes blast pressure and serves as a hearth coke. We also strive for nearly horizontal layers achieved by using manicured angles and minimal discharge time. This prevents material segregation and maintain uniform permeability throughout the burden. Nutcoke can be added to the ferrous burden, especially near the walls, to improve permeability in the cohesive zone and assist direct reduction. Furthermore, fines should be distributed evenly through the radius to avoid concentration in rings, which can lead to inconsistent permeability. Regarding layer thickness, thicker coke layer improve permeability while thinner ferrous layer promote better gas contact and reduction. Ideally, ore layer should not exceed 70 to 80 centimeter at the throat, and coke layer should be at least 34 centimeter. Modern furnace extensively use BLT technology, and which offer significant flexibility with rotating chute and varying discharge position to precisely control the material placement and gas flow. They can even enable spiral charging and precise coke delivery to the furnace center, even though we know these situations are exclusively to meet very abnormal situations. Now, moving beyond distribution is raw material quality management are absolutely vital for stable, efficient operation. As we all know, a major concern is the fine content. Material less than 5 millimeters in size are the killers. So fines critically determine our ore layer permeability. When fines are generated during screening, transport or reduction, they tend to concentrate in a ring, leading to poor permeability and very inefficient gas flow. Now, eliminating the fines also helps preventing scaffold formation, and material blending is another crucial aspect, and especially good blending avoid radial difference in the permeability and dilute the disadvantage of individual component, improving metallurgical softening and melting properties. And for the cook quality, consistency in the size, strength, resistance to chemical attack and residual strength is paramount for stable gas flow and layer buildup. High pulverized coal injection or PCI rate also demand the coke with a even higher cold and hot strength. And finally, the moisture is in the stockyard material can negatively affect the permeability. So managing bean level also helps prevent material degradation and fines. And as we know, let's talk about the gas flow and the permeability control, and which is a very fundamental aspect of the furnace stability. And we know operator constantly monitor permeability factor, which is related to the pressure required to transport the gas through the furnace. So higher permeability correlate directly with the higher production. We also watch the maximum allowable pressure difference delta P. Exceeding this can deteriorate body descent, reduce efficiency and decrease productivity. Blast volume and wear velocity are carefully adjusted based on the blast pressure, body descent and production targets. So maintaining a consistent wear velocity, typically above 283 around 300 meters per second, is important for efficient blast distribution and stable gas flow. Finally, the process symmetry is vital. Ensuring circumferential symmetry in the both charging and the wind distribution means all sections of the blast furnace contribute equally to the process, leading to high performance. Asymmetry can arise from the charging issue, and even in many cases plugging the tuyeres or the slag deposited also resulted from such asymmetric profiles. Now coming to the thermal control, which is also equally important uh, aspects, and moving on to the thermal control which ensure the correct temperature profile throughout the furnace. The raceway adiabatic flame temperature is critical and must be hot enough to ensure molten iron slag, but not so hot as prematurely melt the ferrous material before reduction. This all is known to us. So optimum draft using ranges from 2000 to 2200 degrees centigrade is a good magic wand to maintain by operator to have a consistency in body descent and chemistry. Interestingly, natural gas injection can also allow a very successful operation at lower raft value, for example around 1900, due to increased hydrogen based reduction. As we all know, the top gas temperature should be controlled by staying above 100 degrees centigrade to ensure all water is eliminated from the burden. A low top temperature indicates reduced furnace efficiency. Hot blast temperature is usually maintained at a maximum, as as it's the cheapest way to add energy. Moisture content in the hot blast is typically minimized but can be controlled to adjust the thermal state. Finally, hot metal silicon content or the temperature are the key indicator for the thermal control, and silicon often provide an earlier indication of cooling trend in the furnace. So we must have to uh, keep on focusing these numerical values of silicon along with the temperature also. Our last key factor is the efficient casting operation. A critical practice is dry hearth practice, which aim to prevent liquid accumulation from impacting gas flow in the raceway. It promotes smooth furnace burden descent and enable rapid emergency shutdown without wear blockage. This requires a consistent taphole length, typically 2.5 to 3.5 meter, and high quality of taphole clay. Minimizing liquid accumulation is essential, and poor casting leading to increased liquid level can raise blast pressure, slow burden descent, and increase heat losses. Therefore, continuous tapping, especially with the multiple taphole, keep a stabilized liquid level and upthrust from the gas flow, thereby reducing the flow distortion. And thus we come across the casting operation as a one of the very important aspect to take care of the our furnace consistency. Now coming to our next slide, which is about a very important aspects uh, about to achieve and maintain this comprehensive optimization. How to go ahead, what are the strategies, and one key strategy involved wear injectant, pulverized coal injection, as we know, is one of the major injectant used by our furnaces, and it ranges from 100 to 200 on most of the bigger and modern furnaces. High PCI rates require higher oxygen enrichment. As we all know, this is a good enabler, and as for the injectant like natural gas is concerned, it offer a hydrogen based reduction which can allow a successful operation at lower raft value compared to PCI. And oxygen enrichment itself is crucial for increasing productivity by gasifying more coke and maintaining raft while reducing nitrogen flow. We also rely heavily on instrumentation and monitoring. Modern furnaces use a wide range of tools like a profilometer, burden distribution models, two-ear and top cameras, pressure tap to provide real-time data for adjusting charging practices, and for more complex control, mathematical model and expert systems are used to predict optimal operating condition and assess the impact of changes, as the blast furnace is highly non-linear system. Finally, rules of thumb, and this is also known as, these provide a quick assessment and help develop day-to-day control strategy based on the extensive operational experience. So, in summary, we can say that maintaining and optimizing process stability and efficiency in blast furnace operation LTA is a multifaceted endeavor. It's achieved through meticulous control of burden distribution, raw material quality, gas flow dynamics, thermal control, and costing management. Just recently, what we have discussed now. Uh, the so we can say that the overreaching objective remains clear: to produce economical and sustainable hot metal with a maximum gas reduction and uniform gas distribution, all while minimizing fuel consumption and operational disruption. Is it's a basically our agenda, and it's a continuous balancing act. By mastering these key factors, we ensure the heart of modern steelmaking, bits efficiency and stability, and these can only gives us a low cost hot metal and economically sustainable hot metal.